Hello, this is a video about the introduction to partial fractions, specifically looking at the decomposition of them, and this video is brought to you by Justin Nathanson. You might be asking yourself, why do I need to learn this? Well, while it might not seem apparent now, in the future this will be very useful to you and help you out with integration and Now you might be asking yourself, how do partial fractions work? Well, the basis behind partial fractions is that any polynomial, no matter what the power, can always be factored into linear and/or quadratic factors. Now, what this video is designed to teach you is how to initially set up your partial fractions by decomposing. The first step in breaking down or decomposing partial fractions is to identify if the power of the numerator is greater than or equal to the power of the denominator. If it is, as in both examples below, you cannot break them down into partial fractions, but instead must use long division to. In regards to partial fractions, there are four distinct cases. In this case, we are going to look at rational functions where the denominator only contains distinct linear factors. Now, let's look at an example. In this example, we have x divided by the quantity x plus 3 times the quantity x plus 2. Now, what you need to do is completely ignore the numerator and only pay attention to the denominator. If the denominator is completely factored, you need to break up the distinct linear terms. In this case, we have two distinct linear terms, x plus 3 and x plus 2, and break them into two separate fractions with nothing in the numerator. And make sure to add them. Adding them is essential. You cannot do anything except add these. Now, one base rule that you must remember and pretty much memorize is that the numerator must be a variable that is 1 degree less than that of the denominator. In this situation, since both the denominators, one is x plus 3 and the second one is x plus 2, have polynomials that are raised to the first degree, the numerator must be a polynomial raised to the 0th power, or, in other words, must be a constant. And we represent these constants with variables, starting with a, and then we just go throughout the alphabet and use letters according to how many factors that we had to break the base, or the original rational function into. Now, let's look at another example. In this situation, we have 1 divided by the quantity x minus 2 times the quantity 2x plus 3 times x. Now, in this situation, we have three distinct linear factors in the denominator. We have x minus 2, 2x plus 3, and x. And just like we did in the previous example, we're going to break them all up into their own fraction, where we have nothing in the numerator for now, and we just put each distinct linear factor in the denominator. And make sure to add them. You must add them. That is something you must memorize how to do. And once again, using the idea that the numerator has to contain a polynomial that is 1 degree less than that of its denominator, and since in this situation again, all the denominators have linear polynomials, that means that there must be constants in the numerator. And once again, we represent these constants starting from a, and since we have three distinct factors, we do a, b, and c. Now, let's move to the second case, where our linear factors in the denominator, except there is multiplicity or repeats of them, meaning that they are raised to a power greater than 1. For example number 3, while it may look very confusing, it's actually not. Let's look at the original rational function. We have 3x plus 1 divided by the quantity of x plus 1 raised to the power of 3 times x. Now, what makes this different from the first two example problems that we did is that there is multiplicity. In this situation, we have a linear function, x plus 1, raised to the power of 3. Now, this makes a big difference in terms of decomposing it. For the x, however, since it's all multiplied by x in the denominator, we treat that the same as in the first example, where we just put a blank numerator and x in the denominator, and then we add that to whatever we add next. So, when there's multiplicity, no matter what the linear or quadratic or any type of polynomial is, no matter what power it's raised to, you do the exact same process of building up to it. And the way you start is you identify what the linear function is. In this situation, we have x plus 1. So, what you do, and like I said, no matter what power it's raised to, no matter what's inside the parentheses, no matter what polynomial is being raised to a power, you need to take that base polynomial, like I said before, in this situation it is x plus 1, and raise it to the power of 1, leaving nothing in the numerator. So, as you can see, we have x plus 1 raised to the first power in the denominator of added to nothing over x. So, this is a pretty basic principle of decomposing rational functions. So then what you do is you keep doing this, adding 1 to the power you're raising the polynomial to each time until the power reaches what it is in the original rational function. In this situation, in the original rational function, we have x plus 1 raised to the third power. This means we need to create 3 separate factors: x plus 1 raised to the first power, x plus 1 raised to the second power, and x plus 1 raised to the third power. Stopping there, since the factor that we just decomposed into, x plus 1 raised to the third power, is equal to x plus 1 raised to the third power in the original rational function. Okay, now, when we're assigning what to put in the numerator, we must remember that these are all linear polynomials. And you might be thinking to yourself, we have a linear raised to the power of 2 and a linear raised to the power of 3 in the denominator. Aren't these quadratic and cubic? Well, in this situation, what we do is we pretend that they are linear raised to a power. We only care what's in the parentheses. So in this situation, each of the separate factors have a linear denominator, indicating that the numerators all must be constants, since the denominator is a polynomial raised to 1 power more than that of its numerator. And we represent that with a, b, c, and d. Now, let's look at example number 4. In this situation, we have 1 divided by the quantity x squared minus 4 times x minus 2. And you might be thinking to yourself, I'm just going to dive right in. But you would be wrong. In fact, you would have a difference of 2 squares in the denominator as one of your factors. And this is a big deal, since you can further factor the denominator into x minus 2 times x minus 2 times x plus 2. But to further simplify things, we're just going to write the rational function as 1 divided by the quantity x minus 2 squared times x plus 2. So now that we have completely factored the denominator, let us decompose this. So, we once again have multiplicity in the denominator in the form of x minus 2 raised to the second power. So, the first step, I feel, in this situation would be just to factor out the x plus 2, since there's no multiplicity for it. So, just like before, you leave the numerator blank, and you just divide that by x plus 2. Now, we're going to add all that to the building up of x minus 2 raised to the second power. Like we stated in the previous example, you must start with the base linear polynomial raised to the power of 1. In this situation, the 1 is not labeled since it does nothing. So, as you can see, we have a factor where there's nothing in the numerator, all divided by x minus 2. And we're going to add this to nothing in the numerator divided by x minus 2 squared. And as we are building up, as you can see, we're adding them together. Except this situation, we can stop when the numerator is x minus 2 raised to the second power, since in the original rational function, we only had x minus 2 with multiplicity 2. And like I stated before, even though you have x minus 2 raised to the second power in the denominator, You treat it as a linear function. That's just something you do. And in this situation, that means all the numerators must be a constant. A, B, and C. Now, we are going to move on to our third case, where the denominator of our rational functions contains quadratic factors. Previously, we've only worked with linear factors in the denominator, and now we are moving on to those that have quadratics. So, let's look at example 5. In this situation, we have x plus 1 divided by the quantity x squared plus 2 times x squared plus 9. So, in regards to what we've done prior, the denominators are practically the exact same process as if they were linear. You break them up into their own separate factors. But be careful, you do not do any building up here since there is no multiplicity. Multiplicity only occurs when you have a complete polynomial raised to the power of 2. Instead here we just have a quadratic polynomial. So, as you can see, we broke it up into two separate factors. The numerator divided by the quantity x squared plus 2, and we add that whole thing. Make sure to always add the factors you decompose together into plus x squared plus 9. So, the rule that I stated before, that the numerator had to be a polynomial that is 1 degree less than that of its denominator, well, in this situation, both of these factors' denominators are quadratic, meaning that the numerators have to have a linear version of variables. And the way we represent this is with a, which is just any number, since it's a variable, times x plus b, and we use that form throughout as long as there's a quadratic in the denominator. And since we have two factors that are in the denominator that have quadratics, we just continue the alphabet and go cx plus d. Now we are about to start our final case, where we have quadratic factors with multiplicity in the denominators. Here's our final example, and while it may look confusing, don't worry, it's actually not that hard. Here we have 14 divided by the quantity of x squared plus 4 raised to the power of 3 times the quantity x squared plus 9. So, the first step in this situation would be to, in a sense, get rid of the x squared plus 9 and make it its own factor, since there's no multiplicity in regards to it, and like I said before, we treat it as if it's a linear and do the same thing, where we just have x squared plus 9 in the denominator and we put nothing in the numerator for now. So, what do we do about having a quadratic with multiplicity? Well, we do the exact same process as we did with linears. We look at the base polynomial being raised to the power. In this situation, it's x squared plus 4 being raised to the power of 3. So, what we have to do is, remember like I said before, no matter what power it's raised to, you must start with the base quadratic formula raised to the power of 1. So in this situation, we have to add the factor of x squared plus 9 to the factor of x squared plus 4 raised to the first power. It's not shown since it does nothing, and, raising something to the first power only gives you what number you raise to that power. However, we have to add that, continuing to build up. Remember, building up is very important, and we need to keep adding that to the same base polynomial raised to the power, increasing that power by 1 until that power reaches the same as it is in the base rational function. In this situation, x squared plus 4 is raised to the power of 3, which is so that means we need to start at x squared plus 4 raised to the power of 1, add that to x squared plus 4 raised to the power of 2, remembering building up, and we have to add that to x squared plus 4 raised to the power of 3, stopping there since that is the exact same as what it is in the base equation. So, in regards to the numerators, now that all the denominators are all perfectly created and laid out, like before, we're gonna use the idea that each denominator is quadratic. Although there's quadratics raised to a power greater than 1, making it seem as if it's a quartic or a polynomial raised to the 6th term, we must remember that it's in the parentheses. The only thing in the parentheses matters, which means each denominator is quadratic. And like before, we need to make the numerators a linear term. So, using the alphabet, we start with ax plus b, then cx plus d, then ex plus f, and gx plus. I hope you learned a lot from my video. It's not that easy of a topic, but you did great. This has been Justin Nathanson's Jellyfish Math, and I hope you learned a lot.